Today we are going to start Unit 5. First is the Laurent Theorem. Statement of the Laurent Theorem. Let fz be analytic. Let fz be analytic in a ring shape region. In a ring shape region D bounded by two concentric circles. Bounded by two concentric circles. C1 and C2 with center Z0 and radii R1 and R2 less than R1. Let Z be any point inside D. Let Z be any point in D. Then fz can be represented by infinite series of the form given by fz can be represented by infinite series of the form given by summation and ranges from 0 to infinity a n z minus z naught to the power n sum of n ranges from 1 to infinity b to the power n z minus z naught to the power minus n, where a n is given by 1 by 2 pi I integral over c1 f of w dw w minus z naught to the power n plus 1, and bn is given by 1 by 2 pi I integral over c2 w minus z naught to the power n minus 1 f of w dw, and ranges from 1 to up to infinity. In the statement of the theorem given, fz is analytic in a ring-shaped region D bounded by two concentric circles C1 and C2 with center Z0 and radii R1 and R2. We satisfy this condition. R2 is less than R1. If Z is any point in this D, then fz can be represented by infinite series of this form given by this. This is known as analytic part. And this is known as principal part, where the coefficient a n and bn is given by this. To prove this theorem, we need the statement of Cauchy integral formula for multiple connected region. So first I will give the statement of Cauchy integral formula for multi-connected region. Cauchy integral formula for multi-connected region. I'm not going to the detail of proof. This is your home assignment. Proof is your home assignment. You should solve it. In case of any problem, you should ask me. I will solve it for you. Let fz be analytic in a domain D bounded by two closed curves C1 and C2. Then fz is given by f z naught is given by 1 by 2 by I integral over c1 f of z dz z minus z naught minus 1 by 2 by I 1 by 2 by I minus 1 by 2 by I integral over c2 f of the f z dz z minus z naught where z naught where z naught lies in D. Okay, you should prove this theorem. I will just give the statement of the theorem as I will use this in the proof of the Laurent theorem. So next we are going to prove Laurent theorem. First we will draw the figure. Suppose this is the center of the circle with z naught at center. We will draw a circle. We will draw a circle. Okay, this is the circle with radius r1. We draw another circle of radius r2. Okay, this circle has radius r2. Suppose z is any point here with distance between z naught z is r with z naught as center and radius z naught z. We draw another circle given by this dotted line. So write the function fz is analytic in a ring shaped region D bounded by two concentric circle concentric circle bounded by two concentric circle C1 and C2 with center Z0 and radii R1 and R2 less than R1. Okay, let Z be any point in D. Let Z be any point in D. Any point in D by Cauchy integral formula for multi-connected region. By Cauchy integral formula for multi-connected region we have f of z. Since fz is fz is analytic in the ring shape region D. So fz, by using Cauchy integral formula for multi-connected region, I can write this one: integral over c1 f of w dw w minus z minus 1 by 2 by I integral over c2 f of w dw w minus z. Okay, this is my equation 1. This is my equation 1. For the first integral of equation 1 consider the identity, the identity identity for this integral. I will consider this identity, that is 1 by w minus z, which can be written as 1 by w minus z naught plus z naught minus z, and this is equal to w minus z naught minus z naught, which is equal to 1 by w minus z naught 1 minus z naught w minus z naught. Then I w minus z naught 1 minus z naught. I will bring this to numerator. I will get this one. Next, expand this by using the formula for expansion of this one. I will consider the expansion up to nth term, which is given by this, which you can easily obtain by using expansion of infinite series by Maclaurin's theorem, considering a remainder term up to n remainder term, this one, considering considering theta equal to 1 in the remainder term, I will get this expansion. So I use this formula. I will get, in the next step you can write, in the next step I will get this one, that is 1 plus z minus z naught w minus z naught z minus z naught by w minus z naught whole square plus z minus z naught w minus z naught to the power n minus 1 plus z minus z naught w minus z naught to the power n. In the last term I have this z minus z naught by w minus z naught. Okay, bracket close. So again, if you expand this one, I will get this w minus z naught w minus z naught square plus z minus z naught square w minus z naught cube. Okay, plus dot 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 plus z minus z naught to the power n minus 1 w minus z naught to the power n. Here n minus 1 multiplied with this one, this is n. Here it will be here. If I expand this one will be z minus z naught by w minus z naught to the power n. In the remainder it will be w minus z naught minus z plus z naught by w minus z naught. This cancel out. We have w minus z naught and this one by w minus z naught. This cancel with this one. I will left with the 1 by w minus z, not z, w minus z. That is 1 into 1 by w minus z. Okay. Then put this equation 2. So in next step multiplying by f of w by 2 pi I, and integrating around C2, not C2, this time it is C1 because we are considering the first integral. So integrating C1, we have considered the first integral of 1, we have considered the first integral of 1, so here integration is around C. Okay, 1 by 2 by I integration of C1 f of w dw w minus z. Here it is 1 by 2 by I integration of C1 f of w dw w minus z plus 1 by 2 by I integration over C1 half of w dw w minus z naught square. Here there will be one z minus z naught. One, as z minus z naught is out of independent of w, so I can take outside. Is it? So I have taken this outside, then keep this one. Goes on 1 by 2 by I, here z minus z naught to the power n minus 1 integral over c1 f of w dw w minus z naught to the power n plus here r. The term before this will be z minus z naught. The term after this will be, not before this, after this will be z minus z naught square by 2 pi I integral over c1 f of w dw w minus z naught u. Then this is plus Rn. So right, where what is Rn? Rn is z minus z naught to the power n 2 pi I integral over c1 f of w dw, then w minus z naught w minus z naught to the power n w minus z. Okay, next putting an 1 by 2 pi I integral over c1 f of w dw w minus z naught to the power n plus 1. If I take n equal to 0, this will be 1. So I will, if I put n equal to 0, this will be 1 by 2 pi I integral over c1 fw dw w minus z naught. I will get the first term. Okay. If I put n equal to 0, I will get the first term. Therefore, 2 pi I integral over c1 f of w dw w minus z is equal to 8 naught. Okay. If I put n equal to 1, I will get the second term. So write a1 z minus z naught square. If I z minus z naught not square. If I put n equal to 2, I will get the third term. Okay, that is z minus a2 z minus z square. Here this term will be my a2 and this term will be my a1. Like this term will be my n minus 1. Okay, goes on. Plus r n. Put this some equation. What is the equation? Equation number 3. This is 3 or 2. This is not put equation number here. Give the equation number here. That is equation number 3. We shall show that r n tends to 0 as n tends to infinity. Suppose z minus z naught is equal to r and w minus z naught is equal to r1 where w lies on c1 and w minus z is equal to w minus z is equal to w minus z naught plus z naught minus z which is greater than equal to using this is not greater than equal to, this is equal to, take minus common, z minus z naught modulus. Then again using the property of modulus of difference of the complex number, this is always greater than equal to w minus z naught. This is z naught, okay? W minus z naught, z minus z. What is w minus z naught? It is r1 minus r. Okay. Next, if m1 is the greatest value of fz in C1, then modulus of Rn is equal to modulus of z minus z naught to the power n 2 by I integral over C1 f of w dw w minus z naught to the power n w minus z. Now using the properties of modulus, I can write this z minus z naught to the power n 2 pi integral c1 modulus of fw d modulus of dw modulus of w minus z naught to the power n w minus z. Here this value is equal to r n 2 pi and this value is m1, so this is greater than equal to, and this value is mine w minus z naught is r1 to the power n. Here it is greater than equal to w minus z is greater than equal to r1 minus r, so 1 by w modulus of w1 w minus z is less than equal to r1 minus r. Then integral over c1 not c2 c1 modulus of w. Now in the next line this is equal to 1 by 2 pi m1 r1 minus r, then r by r1 r by r1 to the power n. We know the value of integral c1 dw is the length of the curve, which we have already discussed in complex integral example lecture. So you should go through it. It is equal to 2 by r1, as r1 is the radius of the circle c1. So put this value. This is 2 by r1. So this cancels out. This is equal to m1 r1 by r1 minus r, that is r by r1 to the power n. As since it is given, since since we have considered r1 greater than r, so r by r1 is less than 1, and as it increases indefinitely, it will tend to 0. Therefore, Rn converges to 0 as n tends to infinity, and the series 3 become an infinite series. Okay, therefore 3 becomes integral 1 by 2 by I integral c1 f of w dw w minus z is equal to a naught a1 z minus z naught plus a2 z minus z naught square plus dot 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 a n minus 1 z minus z naught n minus 1 plus dot dot dot, which can be written in summation notation as n equal to 0 to infinity a n naught a naught a n a n z minus z naught to the power n. Okay, and ranges from 0 to infinity. Put this equation 4. Now for the second integral of 1, for the second integral of 1, consider the following identity. Consider the following identity. What is the second integral of 1? Equation 1. Second integral of equation 1 is this one. This is this one. This one. For that, I will consider minus 1 by w minus z. We will consider this identity, that is equal to 1 by z minus w. So rearranging, writing in this way, adding and subtracting the same quantity, it will not create any change. So in next step, you should write this one, then take, in the next step you should take z minus z not common. So this is z minus z not common. Then we have 1 minus w minus z naught, and then z minus z naught. Okay, z naught. So in next step you can write this as w minus z 1 by w minus z minus z naught, z minus z minus z naught, z minus z minus z naught. Bring the term to numerator. This is, will be w minus z naught, z minus z inverse. Okay. Yeah. Again, expand this by using this expansion up to an term, which is equal to this one. So by using this expansion, I will get this one. This is 1 plus w minus z minus z naught plus w minus z naught by z minus z naught whole square plus dot 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 plus w minus z naught z minus z naught to the power n minus 1 w minus z naught z minus z naught to the power n 1 by 1 w minus z naught z minus z naught bracket close. If I expand this one, I will get this z minus z naught, okay, plus w minus z naught z minus z naught square plus w minus z naught square z minus z naught cube dot 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 plus the plus w minus z naught to the power n minus 1 z minus z naught to the power n plus w minus z naught z minus z naught to the power n. If I simplify this one, I will get z minus z naught 1 by minus w minus z naught. Minus minus is plus. So this is z minus z. To just cancel out, I will left with z minus w by z minus z naught. Multiply with this one. Multiplied with this one. 1 by z minus z naught. This cancel out. I will left with 1 by z minus w. That is 1 by z minus w. Round this up. Then in the next line, you should write multiplying by fw by 2 by I and integrating around C2 we get this time we are considering the second integral, so our integration is around C2. So we will get minus 1 by 2 by I C2 half of W dW W minus Z here. If I integrate around C2, this is 1 by Z now this can be taken outside the integral sign, okay, dW Z minus Z not I'm writing here, but this is free of variable of integration, okay. Then second 1 by 2 by I integration over C2 half of W dW Z minus Z naught square. There will be one W minus Z. There will be one W minus Z, okay. There will be one W minus Z. With the variable of integrand, there will be one W minus Z half of W dW plus 1 by 2 by I integral over C2 W minus Z naught square f of W dW, then Z minus Z naught cube goes on, then 1 by 2 by I integral over C2 W minus Z naught to the power n f of W dW, then Z minus Z naught to the power n. This is minus 1, the nth term. This Z W minus Z naught, then Write the last term, which is your Pn, yeah, where Pn become, where Pn is 1 by 2 by I integral over C to W minus Z not to the power n, Z minus Z not to the power n, f of W dW, then Z minus W. Okay. Next, putting Vn equal to 1 by 2 by I integral over C to W minus Z naught to the power n minus 1 f of W dW. In the right hand side, I will get this one 2 by I integral over C to f of W dW W minus Z. Okay. In the right hand side, if I put n equal to 1, this will be 0, this will be 0, and I will have n equal to 1. So b1 is equal to 1 by 2 pi integral over c to fw dw. So I will give this portion. I will get this portion as b1. Okay, as b1. So in next step, this is show b1 is z minus z and b2. If I put b2, this is 2, this is 1. So here I will get this portion as my b1. This portion as my b1. Okay, this portion as b1. So write this b1 b2, not b1. This portion as b2. If I put n equal to 2, n equal to 2 here, n equal to 2, n equal to 2, n equal to 2, this is b2, this is 1. So I will get this portion. And here in the denominator, I will have z minus z naught square. Okay. Then b3 equal to, if I put n equal to 3, this is a square. And this portion is your b3. b3. This portion is b3. So this is z minus z naught 3 goes on. This is b n. If I put n, this is n minus 1, and this portion is your bn divided by z minus z naught to the power z minus z naught to the power n plus bn. Okay, this portion is your bn. Okay. Next, we shall show that. Next, we shall show that Pn tends to 0 as n tends to infinity. For that, suppose z naught is equal to r and w minus z naught is equal to r2, where w lies in r2, where w lies in c2, and the identity w z minus w is equal, can be written as z minus z naught plus z naught minus w. If this cancel out, I will left with this one. So rearrange the term. Using the properties of difference of the complex number, I can write this one. This is equal to r minus r2. Okay. if m2 is the greatest value, if m2 is the greatest value of fz in C2, then Pn is equal to take modulus in both sides. I will get this one C2, that is w minus z naught to the power n f of w dw, then z minus z naught to the power n. Here it is z minus w. Let us check whether this is Pn or not. Yeah, this is the Pn. Now put the modulus. This is less than equal to 1 by 2 pi. Modulus of I is 1. This is C2. This is modulus of W minus Z naught N. Modulus of Z minus Z naught N. Modulus of FW. Modulus of the Z minus W. Modulus DW. Now this is equal to 1 by 2 pi, as this is W minus Z is R2 to the power N by Z minus Z naught is R minus, this is Z minus Z naught is R, okay, is R, it is R to the power N, to the power N. This is M2 less than equal to M2, so I have put here less than equal to M. Modulus of Z minus W is greater than equal to R minus R2. So 1 by modulus of Z minus W is less than equal to R minus R2. So here it is less than equal to R minus R2. R minus R2. See DW. This is C2. Okay. And from the example on complex integral lecture, we know this value is equal to length of the curve. Here curve is C2, C2 is circle. So this is equal to my this one. 1 by 2 pi r by r, r2 by r, and m2 by r minus r2, r minus r2. Here it is 2 pi r2, since C2 dw modulus of dw equal to 2 pi r2. Okay, length of the curve, which is circle, that means perimeter will be the length of curve. So these two pi cancel out, 2 pi cancel out, and this is equal to m2 r2 by r minus r2 by into multiplied with r2 by r to the power n. Since r2 is less than r, so r2 by r to the power n tends to 0 as n tends to infinity. Therefore, Pn tends to 0, tends to 0, tends to 0 as n tends to infinity. Therefore, this series become put this some equation. What is the last equation? Equation 5. Equation 5. Therefore, it becomes minus 1 by 2 by I integral of C to f of w dw minus w minus z naught. W minus z naught z naught. w minus z is equal to b1 z minus z naught plus b2 z minus z naught square plus dot 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 bn z minus z naught to the power n plus dot dot dot. That is, this is the infinite series, which is okay. Yeah. N0, so it becomes infinite series. The n ranges from 1 here, it is 4 to infinity bm z minus z naught, okay, to the power n, which can also be written as n ranges from 1 to infinity bn z minus z naught to the power minus 1. So put this equation 6 using this value of, that means this is equal to minus 1 by 2 pi I integral over c2 f of w dw w minus z. Using equation 6 and equation 6 and equation 4 in 1, in this equation 1 we will get the required results. 4 and 6 in 1 we will get the required result. So using 6 and 4 in 1 we get, what do we get? Fz equal to sum of n ranges from 0 to infinity a n z minus z naught to the power n plus sum of 1 to infinity bn z minus z naught to the power minus n, where our an is given by 1 by 2 by I integral over c1 f of w dw w minus z naught to the power n plus 1, and bn is given by 1 by 2 by I integral over c2 w minus z naught n minus 1 f of w dw, where n lies from 1 to infinity. Okay, this is the required Laurent theorem, or Lorentz series expansion of the function fz above the point z equal to z naught. Hence the proof. With that, I would like to conclude. Remaining will be in the next lecture. Thank you.